In this video, we'll take a look here at example number 4. We're going to be heavily relying on the previous theorem that was discussed, which allowed us to take the derivative and antiderivative of a function which had a matching power series. And we understood how we could model that function, that new derivative or antiderivative. So take a look down here at example 4. We've kind of already established in this section and sections past that for the function 1 over 1 minus x squared, since that looks just like something that's geometric, like an a over 1 minus r, it should be exactly equal to this series on this given interval. But I might, starting from this information, be curious how to express this thing as a power series, and ultimately state the radius of convergence. So I'm going to go ahead and maybe note the following very quickly. I'll start by saying that we see that there is actually a connection between our function f and our other series over here, 1 over 1 minus x all squared. And you might be able to spot what that relationship is. Take a moment and see if you can find the connection between this function here and this new function. Well, one thing that you might notice is that if you were to take the derivative of f, you actually end up with this new function. So f prime is equivalent to what we're working with over here. That's awesome. And what that means automatically is that by the above theorem, we then know that this f prime of x, which is our 1 over 1 minus x quantity all squared, is actually then going to be equal to, and since I started with a function that was equal to this series, and now I just want its derivative, I just have to take the derivative of this series, which is really easy to do, because I would just take the n, bring it down to the front, because that was the power, and then lower the power by 1. Notice I'm taking the derivative with respect to the variable of x, since this is just a polynomial looking thing with x's in it. Remember again though that I'm going to start with my n here at a 1, since I know that my constant term here would just fall off. So this here would represent a function that models, or this is a power series, excuse me, that models our new function. And I can go ahead and state the following. I can say that also the radius of convergence here is still going to be 1, because the above theorem said that the radius of convergence for those new power series will still be the same as what it was before. So we've completely answered this question by using these simple properties of being able to take derivatives of power series. Now, one thing that I might go ahead and just make a quick note of down at the bottom here is that we still don't know what the interval of convergence might be for this power series. In fact, we have a lot of different possible options. This power series might have an interval of convergence of -1 to 1. Notice that it's still centered at 0 and had radius 1. But it could also have a power or an interval of convergence of -1 to 1, including the endpoints. It could also have one where maybe it includes one endpoint or another, but not both. So actually, the interval of convergence might be any of these, and we don't know which one. So we don't know which is correct. When we take the derivative or the antiderivative, the endpoints of our interval of convergence may change. And so all the above theorem guarantees us is that the radius of convergence will remain the same. And remember that the radius has nothing to do with whether or not the endpoints are included or excluded. All right, in the next video, we'll take a look at how we can combine this process of taking derivatives with the process of doing antiderivatives to find even more important power series.